Okay, we have our first question. What is an example of the temporal awareness problem? Okay, so the answer is mistakes old data in a new source as new data valid to the query. So moving on to the next question. Okay, we have quite a few people. Nikhil leading with 944. Let's see who wins. Okay, how do attribution and authenticity differ in establishing trust? For options, attribution ensures content has a cryptographic signature. Authenticity carries every claim is factually correct. Attribution checks if model output aligns with cited source content. Authenticity. Okay. The answer is C and D. Seems like we have an equal split of correct and wrong. Okay, M on top with 1334 followed by Wangmei at 129. What are some methods within the RAG pipeline to make answers more credibly aware? So the answer is estimate source reliability, then reweight the sources, downweighting attention on low credibility tokens during inference. Okay, we have a few people coming up. Which of the following is true under the pluralism objective? Three options. Okay, so 50% of us got it correct. The answer is selected documents tend to occupy regions of embedding space farther apart. Okay, people are coming up the scoreboard and the score has crossed 2000. Please what process describes a black-filled citation? Oh, that's so good, huh? So the answer generation followed by source lookup and then citation attachment. You guys have to study harder. Hopefully next week, this week, but there's no final. Which strategies / metrics help achieve / verify good calibration? I like the memes that. Okay, the answer is pairwise self-consistency and expected calibration error. Moving on to the scoreboard. Okay, I think this time we are going to cross 3000 score very easily. Again, this is very close. Let's see. Okay, what could be some key performance indicators for RAG reliability and trustworthiness? Let's see the winners. Why? Thank you. I want to be on the top of the final question, like quickly pressing the 3 again.
Crazy bell curve this time.
Yes. So that was the second to last Kahoot. You still have one last fastest fingers round. Okay, at the end of today's session. So let's thank Sahej for that feedback for writing the meetings and everything. It's tight competition all the way down to last question. Actually, the scores are only differing by 61 points with first and second position. Yeah, so it's like 0.647. Okay, not bad. All right. So I give the green to Brock. Okay, thanks so much. Sahej, number 1. All right, so let's go on. Okay. Let's go. I'm on the race. That's very narrow. This is for later. Yeah. Okay, so I'll come back to that later. So today we have our very last class, and it seems like we got all of the requests in today, thanks to Ada for doing the last request for week 11. So now we have only week 12 and week 13 left, where we need the polls from you. Okay, so hopefully with that we'll have our things all finished up. The other thing that I'll tell you is that Yong, as the organizer from our group, will be pulling up information on the people's page. Okay, so we'll list you all here and with the term and a link to you, which would be pulled out from either your LinkedIn or whatever. So if you have a specific thing, please let Yong know one way or another. Okay. The other thing is, of course, under projects, we'll take all the projects that have a poster. Yong may be chasing you for that if you never put a poster in steps, and then we'll put them here. So if you want a placing, that will also be noted in the projects page. Okay. So please help populate those things or send Yong those details so we can archive it in posterity. These pages actually do help your namesake get credibility on Google, which means that it's likely that ChatGPT and Gemini will actually know who you are. Okay, whether that's a good thing or not remains to be seen, right? Okay. Anyways, we are going to start with our lecture. So we'll let JF take over here. For those of you who are in the room, feel free to use the pen for annotation. It is a little tricky to use. So again, the way that you use it is you have to first click on the annotation. Now you can annotate chart. Okay, and then you can use the flash again.
I don't know. Can I just move the mouse?
Yeah, you can move the mouse. It's also fine to use the mouse to annotate.
Okay. Yeah, just okay. All right. Unfortunately, we don't have anyone doing speculative brag. But I'll be covering what's the so that's me, JF. Rishabh will be doing the second section, and then we've got Chien over there, and then Manaswini and Yong. So this is my topic, loss in the middle. Let me go into slideshow. All right. I actually have a lot of slides. I've got about 50 slides, so I'm going to have to speed through. And I'm going to try to keep an eye on the time and try to keep it within 20 minutes. So, 10 minutes. Yeah. Yeah. Okay. Let me move the bar away. That's as slow as it goes. Okay, lost in the middle. I'm gonna be covering two main sections. The first one is the actual paper, and the second one is will be mitigations. I was really tantalized by this lost in the middle paper has been around for about 2 years. It came out in 2023, and in the past 2 years, a lot of people have been addressing this issue, and that's why we have so many different ways of mitigating it. Move to the next. All right. So this is the paper itself, lost in the middle. And let me move this guy. Okay, this chart is from a behavioral science website. And it tries to explain this idea called zero position effect. And what's zero position effect? Imagine you're on the train, you're going home, and then your mom calls you and then wants you to buy 10 things from the supermarket and just rattles off the 10 items, right? And before you have time to say anything else, she hangs up the phone. And now you have to remember the 10 items. The behavioral scientists will tell you that you are very likely to remember the first few items, maybe the first 2 or 3 items. That's called the primacy effect. And you're also likely to remember the last few items from the list, and that's called the recency effect. There's no such thing as forgetfulness, forgetfulness effect. I think the authors just put it there for fun. And you notice a U-shaped curve, and the interesting thing is that LLMs are just like humans. They also have the U-shaped curve. How do I go back? I'll just show you this U-shaped curve over here. That's the U-shaped curve. And so the authors of the lost in the middle paper, they've tested LLMs performing on RAG tasks. And they have 2 specific tasks that they've tested on. One is called the multi-document question answering task, and the other one is the key value retrieval. And they pit the RAG task against no RAG setting, meaning just simply ask the LLMs to answer without any supplemented knowledge. And this is what it looks like. You have the instruction right at the top, write the high quality answer to the given question using the provided search results, and then you've got all these document chunks. Okay, it's not just 3, but you have several of these document chunks. And one of the chunks will contain the answer to the question, the query at the bottom here. Okay? And then it will look through the context window, find the relevant one, and give the answer. So that's the multi-QA task. And that's the U-shaped curve. Right? You've got your primacy bias, and then you've got your recency bias over here. The red dotted line is the closed book setting, meaning no RAG. And notice that the middle portion of the U shape, it actually performs worse than without any reference, any supplemented knowledge. Okay. So these are the observations. We notice that the performance degrades when the information is in the middle of the input context. And sometimes the middle part of the performance is even worse than answering without any retrieval. And also, nowadays we have, well, at least 2 years ago, as of 2 years ago, we started to have these extended context LLMs, meaning they have larger context windows, like 4K, 32K, and even 100K tokens. I think 2 years later now, we have even larger context windows. And what they found is that extended context models are not necessarily better at using input context. And these are type of positional biases. And so there's primacy bias where the performance is better at the very beginning context and the relevant information appears at the beginning. And the recency bias is when the performance is better when the relevant info is at the end of the input context. So what can you understand from all this? So the authors stated like this: when we prompt LLMs with longer input context, there is a trade-off, and the trade-off is that you may provide more information to increase the performance that the model must reason over, but it will also potentially decrease accuracy. Lead author of the paper, Nelson Liu, he explained it in a YouTube video. He says that when you're giving more context to a model, you're giving it more information, but you're also giving it more opportunities to get confused about what that information is. You want to provide a minimal set of high quality documents and stop there. These are some of the experimental details. I'm going to skip over a lot of these details in order to speed up. If you look at the details, you can go back and look at the slides. And these are the charts. These are the charts showing how the performance degrades. You can see the U-shaped curve, whether using 10 documents or 20 documents or 30 documents. Okay, so now the authors of the paper want to test what if you don't use natural language, you just wanted to retrieve like bits of information without having to do any semantic reasoning. And for that, they have come up with a task called the synthetic key value retrieval task, and this is what it looks like. It's basically a JSON object with key value pairs, and you instruct the LLM to take this key at the bottom and find the value, retrieve the value from this context. And we put in 75 pairs, 140 pairs, and 300 key value pairs. You repeat that roughly about 500 times and see how it performs. And these are the charts showing the performance. This is your 75 key value pairs, 140, and then 300 key value pairs, which correspond to roughly 4K tokens, 8K tokens, and 16K tokens. Then you notice that the Claude, the standard Claude model 1.3 versus the Claude extended context perform almost perfectly well, but the other models are struggling. And these are the results, the observations. So Claude is doing well, other models are struggling. And to me, interestingly, long chat, which is this last model over here, long chat in the 140 key value setting, when the relevant info is placed at the start, it tends to generate code to retrieve key rather than outputting the value. I just find that really interesting. Yeah. So I think it's just trained differently. Some more details of the experiment. Why are large language models not robust? Okay, so these are some speculations, and so they provide three possible explanations. One is that they've actually tested decoder only models versus encoder decoder models, and they find that all the models that tested are all decoder only models, and decoder models are showing the U-shaped curve. When they tested the encoder decoder models, they find that these are relatively robust changes, but once you go beyond the training time sequence length, the U-shaped curve starts to appear. Yeah, and then they also tested using this query aware contextualization. What that means is that they put the question at the top of the sequence, and they repeat the question again at the bottom of the sequence. And they find that this improves the synthetic key value task, the JSON retrieval task, but it hardly matters at all when it comes to the multi-dot QA. Another thing is that both base models and instruction fine-tuning models show the U-shaped performance curve. Okay, so I think I'm doing pretty good for time. In conclusion, for this paper, in the right, there's a trade-off, which is that you can provide more information to help perform better in the downstream task. potentially you also decrease accuracy. In practice, what this trade-off means is that models have difficulty making use of the extra retrieve of humans. And if you use extended context models with a bigger context window, it doesn't really help. And the performance is nearly identical. So now that we have covered the loss in the middle paper, I'm going to move on to the mitigations. And I've uncovered 4 types of mitigations. The first is prompting. So this is the starting of the mitigation section. The first is prompting. And so this paper called On Positional Bias or Faithfulness for Long Form Summarization. And I'm just going to cover this really briefly. This paper focuses on the faithfulness metric in summarization task. And the findings is that you can actually use prompting. You just instruct the LLM to pay more attention to the middle portion context. And you'll actually be moderately effective versus if you use methods to change the input structure like hierarchical merging or incremental updating. It actually helps faithfulness. It actually hurts faithfulness. So I just find it interesting that prompting alone can achieve that. Move on to the next one, re-ranking and reordering. In the loss in the middle paper, the authors recommend two methods. The first method is to perform effective re-ranking, retrieve documents, and you push the relevant chunks closer to the start of input text. And the other method is to do ranked list truncation. What that means is to retrieve fewer documents when appropriate. You don't try to fill up the entire context window. Nelson Liu, the lead author, explains that, for example, if you retrieve 10 documents and you find that the first 2 chunks have high relevance, but after the first 2 chunks, the third chunk onwards have low relevance, there's a huge drop off, right? Then what you want to do is just get the first 2 chunks and not worry, just leave out the rest of the documents. Now I'm going to cover 3 methods offered by LangChain. And you guys know what LangChain is?
Everyone know?
Everybody
Yeah.
know? Okay. All right. So LangChain offers a few class methods to address loss in the middle. The first one is called long context reorder. So this is very simple. If you use LangChain and you call this long context reorder, you'll simply take the entire sequence of chunks or documents. It'll put the most relevant one on top and at the bottom, and the least relevant ones it will shift it to the middle. So that will help to address loss in the middle. Another method is contextual compression. What it does is that it will reduce the overall length. You try to compress the input sequence, and it does that by filtering. The first method is filtering. It will just remove the chunks that it deems are irrelevant to the query, and you can also use an LLM to summarize and extract the most relevant passages, and this will help to reduce the length of the input and make it easier for the LLM to focus on the key details. And the third method by LangChain is called merger retrieval. You use this when you have multiple data sources, like for example, you're pulling data from different, maybe 10 different databases, 10 different knowledge sources. And so you use merger retrieval to merge together all these retrievals and do the re-ranking. And it will just sort of put everything together and help to manage the context more effectively and potentially reduce the chance of relevant information getting lost. Okay, the next mitigation is model modification and fine-tuning. So we're modifying the model so that it performs better and to mitigate loss in the middle. And for this section, I will cover 3 papers calling themselves found in the middle, no less than 3 of them. Maybe more will appear. And I'll also cover a fine-tuning method called IN2 training. This is the first found in the middle paper. It introduces a method called MSPOE, multi-scale position encoding. And the author said it's a simple yet effective plug-and-play approach, no fine-tuning and no additional overhead. So that's interesting. How it works is that I'll just show you this chart. You see that it's performing quite well, and you know, in the middle part it really this is the multi-dog QA, and this is the key value JSON retrieval. So on both of these tasks, you can see this big performance improvement. There's the baseline, and that's the one with MSPOE. So let me explain how this works. Okay, when an LLM is doing inferencing, there are actually two stages. There's a pre-filling stage and there's a decoding stage. And MSPOE does something during the pre-filling stage. It analyzes the query, it establishes a baseline for attention scores, and then it computes the position awareness score to quantify its effectiveness as well. And then it actively assigns scaling ratios. And that's just a really simple and quick way of explaining it. But there's a thing called rotary position embedding, which has a long-term decay effect. And MSPOE addresses that deficiency. Okay, the second found in the middle paper, this actually came from Cloud AI research, and I find this very interesting. Okay, so what they found is that we know about the U-shaped rack performance, but they also found that the attention distributions also have U-shape. And let me try to explain this. So this is the U-shape of the rack performance, U-shaped curve. And they found that the model attention also has a bias, a U-shaped bias. It favors the beginning and end. When you feed a relevant document in the middle, right, you can actually see that the attention, it is paying some attention to this gold document. You can see the attention going up, but it's overwhelmed by the bias at the beginning and the end. And what this found in the middle paper does is that it does some calibration. It takes C, which is this curve, this W-shaped curve. C minus B is bias, and you get the more accurate result, which allows the LLM to pay the most attention to the whole document. Yeah.
Can you go back to the last page?
This one?
No, the curve.
Yeah.
In the D here is very much depends on B and C, right?
Yeah.
And the delta may not be that ideal, right?
Yes, you're right. Which is why there are some caveats noted in the paper. Let me see. I will cover everything. I'll come back to the caveats. Okay, so what it does is that it estimates the bias by measuring the change in attention, and then it removes this bias by calibrating the attention scores across the retrieved documents. And so this is all about calibrated attention. And so if you can see all these, you can see the charts showing that there's some improvements. The orange is the improved one with calibrated attention, and the blue ones are the baseline. And the paper notes some caveats. The first caveat is that they think that this mechanism might be oversimplified. They fail to consider intricate and dynamic aspects of positional attention bias. It also introduces additional computation overhead. The positional attention may not be beneficial in certain contexts. You may in fact want that bias at the beginning and the end, depending on your task. And also, even though they found that calibrating the attention has some benefits, it still doesn't clarify what the root cause of attention bias is. So that was the second found in the middle paper. The third found in the middle paper is called permutation self-consistency improves list-wise ranking in LLMs. To understand this, let me show you an example of what is a list-wise ranking prompt. This prompt: arrange the following passages in decreasing relevance to the query. What are shrews? Number one, cats hunt small animals such as shrews. Not very relevant. The second one is shrews are mole-like mammals. And the third one is shrews use their noses to find prey. So which one do you think is the most relevant to the question, what are shrews? Two, right? And the next most relevant? Tree, yeah. And the least relevant is number one. So the correct, if you ask the LLM to rank these three, the correct ranking should be 2, 3, 1. But notice that the correct answer is placed in the middle, so it may not perform so well. So permutation self-consistency, what it does is that there is a mathematical algorithm to, if you run this many times, it's gonna, and you rotate the relevant chunk in different positions. After many attempts, it will just keep getting the middle part wrong. So these are the randomized chunks. After going to the LLM, you notice that the middle parts 4, 2, and 3, it'll place them in the wrong places. But notice that there's an order to the ones that are accurate, like 1, 2, 3, 5, and then 1, 3, 4, 5, and then 1, 2, 4, 5. So it runs an algorithm to pick out the ones that are wrong and sort of find the correct ones and aggregate them into the correct sequence. So this is called permutation self-consistency. And these are the improvements. Conclusion is that we can recover the true ranking order under arbitrary noise distributions with enough observations and at least one correctly ordered pair in each observation. You only need one correctly ordered pair for it to be able to find something to reorder it correctly. Now I'm going to talk about the next paper, IN2 training. This comes from a paper called Make Your LLM Fully Less Complex. Okay, so this is about, it's similar to the attention calibration thing. And this is similar to, it is a kind of, I think it's a kind of fine-tuning type of training. And the hypothesis is that the loss in middle problem comes from insufficient explicit supervision during long context training, which fails to emphasize any position in a long context can hold crucial information. And the explanation for why the primary bias occurs is that during supervised fine-tuning and alignment, the system message, which strongly influences the generation of the response, is typically presented at the beginning of the context. And as for recency bias, they think that this might be because during pre-training, when you predict for the next token, when you're predicting the next token, you're more likely to be influenced by the few nearby pre-tokens. So meaning the tokens at the bottom of the sequence rather than the long distance tokens at the start or in the other parts. So what this fine-tuning method does is that it rotates all the it generates synthetic long context QA data set. It generates a synthetic long context QA data set, and it requires the correct answer is a short sequence of roughly 120 tokens within a long context of 4K to 32K tokens. And they also do another pass where you have 2 or more short segments that need to be moving over. And so you rotate the relevant chunks throughout the context, and you do fine tuning. And they do it on this Tro 7B model, and they after doing the fine tuning, they come up with a new model called Fill in the Middle of Film 7B. And you can see that the orange is the improved performance versus the original, the gray color one is Mistral 7B, the original unmodified model, versus GPT-4 Turbo. So you can see the improved performance. And so it helps to reduce the loss in the middle problem. And the result is that their model, Film 7B, achieves comparable or even more robust performance than proprietary models such as GPT-4 Turbo. Okay, finally, the last part, and I've exceeded by a little bit. New architectures, this will be really quick. New architectures beyond the standard transformer. Just 2 months ago, October, and iClear a new paper called Differential Transformer was released. It's a new foundational architecture for LLMs. And how it differs from the standard transformer is that it replaces the softmax attention with differential attention, while everything else is kept more or less the same. And it improves performance by amplifying attention to relevant context while filtering out noise. Okay, so what is good at is long sequence evaluation for increasing context. It's good at using increasing context, and it outperforms transformer in information retrieval and in context training. Also mitigating hallucination and improving mathematical reasoning. And you can see how it performs. This is the normal standard transformer. This is the new diff transformer. You notice that there's attention noise at the front and at the back, and the attention noise overwhelms the correct answer, which is in the middle of the graph. And whereas the diff transformer amplifies the relevant signal while reducing the noise at the beginning and end of the sequence. And that's diff transformer. And just last week, I saw something and I was really excited by this. Google has solved catastrophic forgetting. So no more model checkpoints. This new architecture can do continual learning. So instead of having to retrain from the beginning from scratch and releasing a new model every few months, this new nested learning model, they call it the Hope model, can just keep on learning without catastrophic forgetting. And this is how Hope performs. So it does well with long context and extended sequences. But there are some caveats. I saw the paper, no model has been released yet. Not many details available yet. So, and it's still early days, but it looks promising. And I hope something comes out of it. And that's the end of my presentation. I hope that you will remember my slides from the first. I hope you remember Yong's slides, which is the last. And maybe all the best for the middle presenters.
Okay, so thanks, Jeff, for your presentation. Weekly times, we won't have that much discussion, but I think Aran has put some points on the general channel. So please go ahead and engage your discussion catalysts, especially for those who want to get more out of the course. So Rishav, I think you're online. Can you hear us?
Hey, Prof. Yes, just give me a second.
Okay, let me take the screen. Is that okay?
Yeah, wait. Share screen.
So please make it memorable, as JF has says that you have to mitigate your loss in the middle problems.
1 second. Presence screen. Yeah. Screen share. Is my screen visible, guys?
Yes.
Oh, great. Okay, so I'm going to essentially talk about advanced retrieval. I think Jeff mostly covered all the previous required concepts. So advanced retrieval essentially comes right after. Just give me a second. I'm not being able to navigate. Um, Guys, what's the quick command to go to next page? Should be space, right? Yeah, yeah, yeah. Is it changing the
Yes.
screen?
Yes.
Yeah, great. So, essentially, I wanted to start with why we are doing advanced retrieval layer, or like what is essentially retrieval doing. So once the user asks the query, um, uh, either we directly pass the query to the LLM, or rather to the let's say the vector DB to find out the relevant documents, or we try to understand the query and expand it and maybe change it in ways like, for example, there's ways of query expansion. Like, for example, if someone asks questions regarding let's say finance and legalese uh, combined into one, then maybe we will understand. For example, if the question is, could you tell me what are the uh, capitalistic laws that are being passed out? So the query could be expanded in the form of, okay, what is capitalism? And the other thing is how laws are really passed out, something like that, and then get the basis of the question that we are using. So that is step back. Then uh, expanding the query could be in terms of subqueries, where you find out different domains that are being mentioned in that particular query and give more relevance. Now, once you have the query, however you want to modify it, you want to use it to retrieve better documents. Now, as it's written, that why we use it. So the retrieval layer is essentially the main bottleneck in modern RAG systems. Many think that it's the generative layer where you are using the state-of-the-art LLM models to generate the final answer. But many papers have found that if you improve the retrieval layer, you can dramatically improve the quality of answers that are given in even for high-stake domains like healthcare and policy making. So simple keyword or semantic search alone creates three failure modes. Essentially, there could be like, for example, the we use BM25, right, for keyword search. So that's a good method, but it could create vocabulary mismatch between query and documents, brittleness in ranking scores. But then again, when we do dense retrieval, there are many high stake domains. For example, in healthcare, or even let's say in technical jargon, if we want to search the exact Python 3.1 to docs, then we want the solution from that particular version itself. So that's where dense embeddings fail. So that's where we have found that it's very important that we come up with more combinations. For example, that is hybrid search here using uh, BM25 and dense vector embeddings essentially. Then why now? Because right now RAG is being used more and more in big enterprises, and there the database has scaled from tens of thousands of documents to millions and almost billions of documents, because they will have their own legacy data which they want to sift through using AI. And so for that, RAG really needs to come up with better retrieval layers. and only dense or only sparse doesn't help. So how we do it? We augment queries for semantic richness, execute parallel retrieval across sparse and dense methods, fuse rankings adaptively. So, for example, generally we use a lot of numerical scores. For example, map. Then the other is NDGA, and recall is obviously there. But apart from that, there is like ranking. I think the next speaker will be talking about efficient re-ranking, where we can use such ranking scores as RRF, which are very simple and can be used across all domains and very diverse situations. Now, each layer compounds the effect, right? And essentially, after that, we will be retrieving the documents, and their re-ranking step will be happening, which the next speaker will be talking about. So, after that, I essentially wanted to talk about where exactly in the RAG architecture do we consider advanced retrieval. So once we first, so if for example an engineer is wanting to check, hey, do I need to create a RAG for a particular problem. We need to first check if it's what kind of a problem it is. Do we need RAG for it or not? Then we need to check what is the number of documents we need to fetch, like relevant documents. Is it top 20, is it top 100 or top 1000? And according to that, we need to make our decisions. Once we have figured that out, we check that do we want to only do something like a keyword matching? Do we want to do something like dense semantic matching or something in between? And after that, we also see what kind of embedding model we will use. Like, for example, should we use OpenAI's model or BGN3, or I guess Hugging Face is also has a lot of embedding models that we can use. Recently, Voyager has come up with very good multimodal embedding models. So that is the other decision that we make. And after that, query augmentation strategy, which can also be a part of advanced retrieval, because before retrieving, we update or expand the query according to how we want to retrieve the documents. So if we get a certain query, it doesn't have the relevant keywords, maybe we could ask the LLM to append it with important or relevant keywords of that particular technical domain. So for example, if we are trying to search or debug or troubleshoot a problem, rather than saying how to solve this problem, if we write it in more technical terms, like how to troubleshoot Python 3.12 version, this problem, then it will be easier for the RAG to really find that particular document. And that's where essentially advanced retrieval fits in the entire architecture. And after that, once we have the documents, we rank them, and then re-ranking comes up. So that's mostly it. So I'll be basically talking about 2, 3 papers where advanced retrieval has been used. The number one is where 3 different kind of index types have been used. One is BM25 index, which is what I was talking about, simple keyword search. The thing with simple keyword search is it's very quick to do, but it doesn't get the exact semantic match that we need. So dense vector comes and really helps with that. But what these researchers have found, that there's something called sparse encoder index, which is different from both PM25 and dense vector, which could be used to map both documents and queries into high dimensional sparse vectors. And this really balances semantic understanding with efficiency. The challenge with sparse encoder is that it is slower than dense vector. Like KNNs, you can create very quickly, but sparse encoders are slower, but they give better accuracy. So these are some of the decisions that we need to come up with. And then hybrid query strategies is essentially what kind of documents it's trying to search for. So one example is, for example, best field means that if there are n documents, rather than as result fetching all the n documents where a particular keyword has been occurring, it tries to find the only document where the most number of occurrences or the highest chance of having relevant information for that keyword and that query is present, and accordingly that's a way of fetching essentially. Most fields is the direct opposite, where you essentially fetch all the documents wherever this keyword has been occurring, irrespective of how valuable the data in it is or not, or even if it's repetitive. So these are some of the strategies. And what we have found is that the best strategy is essentially sparse encoder plus best fields. So that gives almost 50% plus F1 improvements over the other. Uh, so there's essentially 12 kind of strategies we have used. So apart from in the other 11, this one really stands out. So essentially, if we can create the sparse encoders before uh, before the query process starts, it will really help if we use the sparse encoder plus best fields to give the best bang for buck for the RAG project that we're going to build. Some of the limitations are that it is extremely structure heavy, so it needs a lot of metadata to work well. If there is no good metadata, it really doesn't work that well. Apart from that, the storage speed issue is there. So dense indices need 50 GB versus sparse is 10.5 GB with no clear enterprise deployment guidance. Though it does help in certain ways because it proves that retriever is more important than the LLM that generates the answer. That we should really focus on better retrieval compared to using bigger LLM models to answer from the documents. And yeah, that's the first paper. Did anyone have any questions?
Yes, I have questions. Can you hear me?
Yes.
Can you go
Yes.
to the page you have a 59?
This one.
Yes, no, that's not. Decisions.
Okay.
Decision.
I got it. Yeah.
And you mentioned about embedding model selections. Here, would the embedding model fine-tuning be also part of the decisions, or is that less effective to be considered here?
So I think when we are doing retrieval, essentially the embedding model will also be important in terms of the cosine similarities that we can get and the semantic meanings. I don't think it will be directly relevant to the advanced retrieval strategies, but in terms of deciding how well the entire retrieval section is going to work, I think embedding model is going to be an important point. So I think, maybe I should have made like key decisions in retrieval section rather than advanced retrieval.
Yeah, no, my question is actually whether the embedding model fine-tuning should be important or not.
I guess so. Yeah, like it should be part of the retrieval strategy because the cosine similarity that we have with the documents will enable us to retrieve better documents, right? Like so that's like my understanding.
Okay. You maybe next page.
Okay.
I think you talk a lot about sparse encoder index here, right?
Yes.
The concept is really similar to embedding itself, right? What is the difference? Or just confused that?
So sparse encoder is essentially how to explain. So it's slower than dense index essentially, but the difference is that it captures the relationship between the uh, uh, user query and the documents better.
Isn't that
So
type of embedding?
yeah, essentially, yeah. So sparse encoder is an embedding actually. It's not different from it's different from BM25. So this is also a kind of encoding which is sparse than the dense embeddings that we create using, for example, KNN clustering. These are dimensional vectors where like most values are zero essentially, except the most relevant expanded terms. It's like, for example, in NLMs, when we try to find the most important features out of 1,000, right? So we only flag the most important features and the others are just made blank, zero. So something like that. So essentially, these are embeddings themselves, but have a lot more zeros.
Yeah, I get it. So it's a much more sparse, right? But my confusion here is actually, you get two embedded in a way.
Hmm.
How do you deal with that? Because you have two now, right?
Yeah, so I have dense vectors, so that's the thing. So what they have found is compared to dense embedding, sparse embeddings work better in terms of semantic matching with best fields.
Okay.
So sparse encoders are also able to hold the semantic meaning and find relationships. The issue with sparse encoders is that they take more time to create, so they won't be as fast as dense vector encodings that are created, where we match them as well. So it's mostly similar. The only thing is they have found sparse encoder gives better accuracy at the cost of speed. Dense vector uh, is faster.
Okay. I mean, nice. So this is probably more complex. Anyway, thank you.
Sure. Thank you. Hope I was able to help you out.
Alright, I'll put a link on the general channel, that you can read through that. This is a embedding type that was put out by a particular company. So you can also read it with a grain of salt, because maybe it hasn't been replicated as much. So you can take a look to see whether there have been any peer-reviewed academic papers that also discuss this embedding.
Okay. Sure. I guess I'll continue then.
Yes.
So essentially, after that we come to hide. So well, the paper had a long name, but the essential goal was that how can we make RAG systems that can work on different um, uh, diverse domains, essentially the better word would be, which have a lot of complicated terminology without a lot of fine tuning needed. So what we have essentially found out, I would rather just put it into a concise statement rather than going through all the paras, is essentially we create a hypothetical document. So the moment the query is made by the user, it is put into certain categories. Now, in this particular paper, it has not been mention that they use an LLM or anything for that. It's more like they kind of human annotate those queries as this is like a uh, uh, query about multilingual uh, context, or this query is about some scientific document, or this query is like a general web search query. And that instruction and that particular query is passed into something called an instruct GPT, essentially an LLM model, which generates a hypothetical document. Now, once that hypothetical document is created, we use something like a contriever, which is essentially uses unsupervised contrastive learning to create a document, uh, yeah, document to document similarity. So what it does is that it will rather than trying to match a query with a document, which the literature review of this paper has found that when you try to match a query with different documents and find the cosine similarity with them, if that query belongs to very like a highly technical domain for which the models have not been trained, the cosine similarities don't match well because the query might be very simplistic and the RAG that is, or rather the database that has been provided by that company might be extremely heavy with technical jargon. Now, if you use something like an LLM before that, which has a wide idea of different genres and different domains, it might be able to create an answer which is similar to what might the actual answer look like. So it will help in creating better cosine similarities and thus be able to fetch better results. So instead of using the query to fetch the documents, they are creating a hypothetical document and using the common terms or the structure of that document to fetch better documents, especially in very highly technical or highly sophisticated domains. So an example is something like this. I've just like picked this example and used Notebook LM to create one. So yeah, before that I'll just go with this. So essentially, if this like a web search, they will write a passage to answer the question. If it's something like about COVID-19, they will say write a scientific paper passage answer to answer the question. And like they haven't mentioned the entire thing, but something like to refute or accept the claim. And then if it's so they have also done it with multilingual like different languages, so like Swahili, Bengali and Korean, and they work well. So one example would be for example the query. Let me go to the query. Yeah, so how long does it take to remove the wisdom tooth? So for that, a hypothetical document could be something like this: wisdom tooth removal, this and that, and the surgeon Dr. Elena Vance. So essentially, what that contriever or that encoder that is trained on contrastive learning will like pick up is core concepts like wisdom tooth removal surgery. Procedure duration is generally between 30 minutes. Complex cases involve impaction can take 20 minutes or longer, and it will remove all these extra or rather the hallucinating details, like for example names, nouns, 2023 interview and these kind of things, and thus help in making the document to document matching. Now a few limitations of that it has been found is that it doesn't work well on low resource languages, because the LLM is not well trained on those languages and thus not able to create good documents which are a good representation of what the actual answer might be. And apart from that, the uh, score or rather the accuracy of this Hyde model has been found directly corresponding to what kind of instruct models that we use to create that hypothetical document. So better the hypothetical document, better the answer. But since it depends on bigger models, it has limiting accessibility. But it still does matter because this enables for bigger production companies to run quick POCs, because rather than fine tuning LLM models or basically the vector DBs that does the cosine similarity, so creating models that can understand that particular domain knowledge better, they can simply use hide and quickly check if RAG is working for them, how they could, embed AI into the system. So this is like a really good plus point for such use cases. And it also raises a very important question that all the RAG models, or mostly the RAG models, well, I won't use their terminology, but many of the RAG models that we have seen have been using the numerical score of like cosine similarity to find out how good the RAG model is. But if we find that we really don't need the query and the document cosine similarity to really have great RAG models, then should we really just focus on making better hypothetical documents rather than worrying about these numerical relevance scores? So that's mostly like something that the paper raises, like a philosophical question to think about. And yeah, that's about Hyde. how it can help in advanced retrieval. So in one sentence, essentially it helps advanced retrieval by creating a hypothetical document and then using that document to retrieve better matched answers or documents from the DP. And finally, there's Telerag. So essentially, the thing with Telerag, it's more hardware layer. So the thing that we have found is as we grow the number of documents, if we want to make these vector matchings, they were mostly done on the GPU. But since the data is constantly increasing, it is important that we find out ways we can leverage the CPU. So as you see, the ideal scenario is where the CPU is not used and directly the GPU is used for, well, the pre-retrieval generation where you improve. So essentially, pre-retrieval generation is where the user gives a query, you improve that query, and then use the normal vector DBs and embeddings, whatever you have, to get the documents and then get the answer from the LLM. Now, that has been seen that it has a very high cost because it's extremely expensive to keep so many documents in the GPU. So your GPU cost really raises and it's not cheap. But for CPU, which has cheaper memory, you can use something like CPU retrieval instead of GPU retrieval of the documents. But it has been seen that the latency is extremely high because CPU is generally way much slower than the GPU. Now, for that, Telerag has come up with a advanced retrieval strategy where the moment where you are forming that better question that you're going to use to retrieve the documents, it prefetches some of the documents from the GPU itself that that currently exist in memory. Like for example, some of the documents that were fetched in the previous question are currently being reused and checked if they match. If there is no match or less matches, then it again CPU retrieval is used along with GPU retrieval. So both go parallelly and try to get as many records as possible. So you at start have a lot more answers that we can get from prefetch and then passed on to GPU retrieval. So then GPU can just work on the records that are passed by the CPU during the pre-retrieval generation computation. And then during that time, the CPU can then find the other documents that might match and finally do the post retrieval generation. So you can see the CPU retrieval takes a little bit more time, but that's still doable compared to just using CPU retrieval. So that's mostly Telerag. I think what we do need to maintain is the IVF clusters. So IVF is like inverse indexes that are used, and these are essentially used to map the documents. And apart from that, there are a few design decisions like sorting done on GPU, CPU retrieval, CPU sent distances. So essentially, where should the sorting be done? How many rounds of prefetching should there be? Batching queries, and this is mostly like a few of the design decisions that could be made. And I guess that's it. Apart from that, I think there is one final advanced retrieval technique called Colbert. I think the next speaker can pick that up.
Okay,
So
let's try
that's
for. Okay, we're gonna take a 3-minute break first. So anyone who needs the toilet or wants the water, time to do that. If you have questions or you just sit around, you can engage answer questions on the general.
Sure. Professor, then I will stop sharing the screen then.
Yeah, okay, you can stop, we'll advance the slides on our side. Thank you so much, Rishabh.
Sure.
How are you there?
Share this to per month or
Yeah, it would be visible on the screen, there's only one to here. If you have a laptop, I would just bring your laptop up and show. Pages. Hi, how are you online?
Hi, Professor Ming, do connect me?
Yeah, I was thinking towards the end, maybe you can also say a few words about what you want to get out of the course, how we want to close it. So we're done with all the sections, but anytime you want to add a comment, please just unmute. Is that okay with you?
Sorry, I did not follow entirely. Do you mean the questionnaire or comment?
Yeah, so anytime after each section you have a comment, just unmute and let us know.
Okay, sure.
I know we're going to run out of time today, but I think it's the last section, I mean, the last
Mhm.
session, so we should go to around 8:30 or so. So we'll try to end with the last Kahoot. But after the last Kahoot, maybe I'll ask you to say a couple words. Is that all right?
Mhm. Okay, I got it. Thank you.
Okay, thanks. So Chien Hao is back. So I think we'll start with Chien Hao's part now, so which is the list and start. Yeah.
So you guys can hear me on this, right? Yeah. So I'm gonna talk about efficient reranking. So Rishabh talked about how if one can kind of speed up different techniques, speed up retrieval, and typically in the RAG pipeline, in a RAG sys pipeline, there's two steps. One is retrieval from a database of sorts, and then after that, the third is reranking. So typically retrieval is done in a way such that a query, one way to do retrieval is to have a query be feed the query into an embedding model to get a single vector, then feed the document to embedding model to get a single vector, and then one can do like cosine similarity on that, or like nearest neighbors in the vector DB. And while this is fast because one can kind of pre-compute all the documents at the side, then just use the query to query against all the pre-computed vectors, it does lose quite a lot. The fact that we use dense embeddings here, where every document gets condensed into just a single vector, although the vector is quite high dimensional, it does lead to quite a lot of loss of semantics and meaning. So typically we like to retrieve candidates from the vector DB, and then subsequently we re-rank the candidates so that we when in the process of re-ranking we are able to capture more of the semantics and details of the document.
and the document query interaction. So typically the ranking is done using something like BERT, bidirectional encoder. And so turns out re-ranking is actually quite an important step. In the HyperRec paper, which I'll show later, they actually have this graph over here where they kind of define the notion of data of document bound and model bound, which they abbreviate as E-bound and M-bound. So for those who are familiar with systems, there's a notion of CPU bound tasks and IO bound tasks, where CPU bound tasks are basically CPU bound tasks versus IO bound tasks refer to whether the CPU is the one that's the limiting factor or the IO is the one that's the limiting factor. And over here they have they define a similar notion where they talk about how whether the number of documents versus the quality of the re-ranker model is the limiting factor for the effectiveness of for this exact match metric. So over here they did a small experiment where they tried different re-ranking models. So the brown one is supposed to be the better model, and then the purple and the red ones is supposed to be like poorer ranking models. And I feel like the data here isn't very conclusive, but they kind of use the fact that the brown diverges from the purple graph a little bit more beyond the number of beyond 5 documents. They kind of use that notion to say like that before 5 documents, the effectiveness is limited by the fact that we haven't fetched enough documents, and after 5 documents, the effectiveness is limited by the fact that our ranker model is not good. So although I don't feel like this is that conclusive evidence, but I think their definition of D-bound and M-bound over here is something that's worth considering and worth further investigation. So anyway, their point here is just that the key takeaway is just that re-ranking is important, and and there's also this link that talks quite a lot about re-ranking. So re-ranking is important, but unfortunately it's slow. So I'll talk about how one can improve re-ranking. And the key reason why re-ranking is slow is because the document is typically quite a large document, like maybe on the order of thousands or hundreds of tokens, and query is typically quite small. And when we do the re-ranking, we need to compute pairwise attention interactions between all the query tokens and the document documents. So the document tokens. So this roughly flash attention and all that aside, it's roughly like ON squared, and it scales badly. So back to Rexis, the key idea over here is that the 2 techniques I'll talk about is techniques to improve re-ranking. So the first paper is HyperRec, and I'll cover HyperRec for maybe like 30% of the time, and I'll talk more about Covert because my understanding from friends and what I hear online is that Covert is actually closer to the state of the art for REC. So so HyperRec is in the HyperRec paper they essentially propose that traditionally they essentially propose a decoder based re-ranker. So traditionally we use BERT, which is an encoder based re-ranker, but typically we use encoders because we believe that the effective is more, it leads better results. But HyperRec claims that they can achieve competitive results with decoder-based models. And because they use decoder-based models and they kind of prove that, or they show decent evidence that decoder-based models are just competitive, because they use decoders, they can exploit a lot of optimizations like KB cache reuse, and in so doing they improve the throughput. So that's why they make re-ranking more efficient. So a bit of history and a bit of a recap. If you guys are probably familiar with this already, but I'll just mention as context. So in the first attention is all you need paper, it was essentially solving a translation task. And when they proposed a transformer, they proposed it in the following form, where you have one encoder on the left over here and one decoder on the right over here. So the source language we put in as input into the encoder, and the encoder is bidirectional full self-attention, meaning that all the tokens attend to each other. And essentially that that helps contextualize each token. It then helps contextualize each token, and the embedding that's produced would capture the semantic meaning of the words around it. So this was then fed to the decoder in one of the middle layers here, and this is called cross attention, and the decoder model will be the one that generates the translator output. So what the community found was that this is effective. The encoders and decoders are not just effective when they're put together, but they're actually effective by themselves as well. So the Google team found that encoders are effective for things like classification, embedding, and re-ranking, which and the decoders, people found that decoders are useful for things like text generation, and that led to ChatGPT. So more on the encoder side, why I like to give a small example for why we think that embedders are good for encoders are good for embedding. And the main reason is that the bidirectional attention is useful in such a, for example. So in this case, if I say the high interest rate in Japan, if we try to generate an embedding for the word interest, for the token interest, the decoder only model will essentially only see the high interest, and without the future context, there's no indication what that interest might mean, whether it's because mass could totally be like rate, right? Or mass could be like in up, and that would completely change the meaning of the word interest. So this is a small toy example for why historically encoders has performed better for embeddings, because they are able to capture both the context from in front and behind the word of interest. And there's a very nice Julia Park video recently published that I really enjoyed the historical narration. So I really recommend it. So so the core idea of HyperRec is that we can use decoder models, we can use decoder-based models for re-ranking as well. And the one key thing that they do is that they claim that if they put the document before the query, so typically in encoder-based models, we put the query first and then the document. But the claim was that if we put the document first and then the query, it helps the decoder model essentially be competitive. So that's one of the changes they made, switching the order of this. And another reason why they did this swapping of the document query is because by putting the document first, it actually enables you to kind of pre-compute the document and store the KB cache in some other form of storage. So what this means is that so essentially by putting the document first, if they feed it into a model, they can take all set of all documents and feed it into decoders without the query yet, and then they just pause at the query, and then when they pause right before ingesting the query, that is essentially they take a snapshot of the KB cache over there and store it in some big data storage. So the KB cache, the KB will be quite huge, but if they store it in, but by saving the KB cache, they avoid needing to recompute the key value attention scores for the document whenever they want to do a compound query like that. So that's one of the key ideas that they use to essentially speed up re-ranking by kind of computing all the document KB caches offline. And the only reason why they can do this is because they are using a decoder-based model, because KB cache doesn't work for encoder-based models. So so they use the LM cache framework, which supports certain storage backends like NVMe or Redis. And here are some other optimizations that they also perform. So as mentioned previously, they pre-compute the KB cache for documents and store them in a big storage. And they also use group query attention to reduce the KB cache memory requirements. So and they optionally turn on quantization for the KB cache. In the final JAMA 2B model, they did not do this, but it's an option that you can use. They mentioned something about dynamically balancing retrieval and generation, meaning that the GPU is when the GPU has the decoder performs both. The decoder performs both retrieval and generation, and then they claim to have some kind of way to balance the workloads. I couldn't find details in the paper about how they balance it, but the code is open source on GitHub, which I'll show at the end. So perhaps it might be in a code base somewhere. Another thing that they did mention was the static attention layout, which is illustrated in this drawing over here, where essentially allocate a fixed size for the document and the query, fixed memory chunk for the document and the query, regardless of how big the document and query actually is. And they kind of fit it like this from both ends. And the claim is that this leads to better kernel fusion. I have a slide after this explaining a bit more on what kernel fusion is. And lastly, the use of the FAISS Facebook AI similarity search for retrieval. So a quick note on what kernel fusion is. Recently, there's a talk. Very recently, there's a talk on how on making GPUs faster by did this video over here. And essentially, the key idea is that when each of these are kernels, right? So the gray box over here is kernel, the other norm is the kernel, value is the kernel, and add is the kernel. And if we want to feed the output of one kernel to the other, we need to first store it to GPU memory, and then we need to load it for the next kernel. So this load and store is kind of wasted because if we know ahead of time that we're going to do value right after the norm, then we kind of just fuse it together into a single. We can fuse these two kernels into a single combined kernel. So that kind of it's kind of equivalent to saying like instead of the functions storing the result in a variable or storing in memory, you just combine the functions. It's kind of like a compiler optimization. And this is enabled in PyTorch using torch.compile. And my understanding is that there's also equivalent in CUDA called CUDA graphs. So yeah, so I don't have the details for why static attention layout leads to more kernel fusion being possible, but I think it's reasonable to expect that basically if your arrays are kind of static size, then the compiler can be smarter about things. So yeah. And yeah, so the key results are here, and essentially they showed that VGE is an encoder-based model, Gemma is an encoder-based model, and then HGemma is hyperrect Gemma. And they essentially showed that you can see that the results here are equivalent for Gemma and hyperrect Gemma, but the throughput is faster for hyperrect Gemma. So yeah, and you can see that the results for these are competitive with VGE. And so yeah, so that brings us to Cobalt. Yeah, so Cobalt can also be used to do full retrieval as well, but I'll talk about it mostly in the case of re-ranking, but it's a similar concept. So the key idea is that previously we will use BERT to do re-ranking. We do a token to all the tokens attend to all the tokens in the attention scores, the attention mechanism. But it turns out that if you take inspiration from BM25, where BM25 actually performs decently in some cases, if we take that inspiration, we realize that what we really want is the in-between between the all-to-all interaction and the representation-based similarity here. So in this extreme case, we take an entire document and turn it into a single vector. In this extreme case, we compare every token with each other. But actually what we kind of want is, the idea of covert is that we want to make sure that the query gets to interact with each other, and then at the end of it, if the query is size n, we want n vectors, and we use the same for the document, and then subsequently we can compare token level interactions, but without needing the entire the entire interaction here between the query and the document. So essentially, this helps us achieve some level of contextual understanding of the document and the query, but at the same time, it allows us to process the document offline, and then subsequently use maximilarity metric to fetch the documents. So a quick example will be here, where we have, so for example, if to encode the query, Cobalt would first pair it with the CLS and Q token and pair this with mask, and then it's fed to BERT where it produces, so the query is truncated to 32 tokens filled with mask and cut off if it's too long, and it produces the 32 embeddings, and then this is fed to the linear layer where it projects it down onto 128 dimensional embeddings, and this linear layer is fine-tuned. And so yeah, so they normalize it so that just use dot products to find constant similarity. And essentially the reason why we can down project it is also because we are having one vector for each token. We're not summarizing the entire document with one big vector. So essentially they are saying that one big vector is performing worse than many small vectors. And there's also some ablation studies to show this later. So we do basically the same thing for the document encoding, except with without punctuation. Yeah. And to calculate the similarity scores, we perform this thing called maximality, where we take the maximum over the document and then we sum over the query. And yeah, I think I can show the ablation studies to show that this is important. So this essentially allows us to compute for each document we can do it offline, and subsequently we do not need to recompute it for every new query that comes along. And so here's how they perform training. They do something called the pairwise softmax entropy loss, where essentially for every query they're given a positive document, negative document, and then Colbert is fine-tuned to produce scores for these documents such that the positive document score is higher than the negative document score. And the more confident is of that positive document score higher than the negative one, the more confident it is, the lower the loss. So pairwise softmax just means that each of them has a score, they do softmax on it, they calculate entropy. And they also use the Adam optimizer. And I think importantly, they found in the core paper, they found that a few parts of this algorithm is important. So namely, they did ablation studies where they replaced certain critical parts of this algorithm with other algorithms. So for example, they performed one where they replaced instead of having each token have its own embedding vector, they use a classification token, and they took that classification token as a vector. Essentially, they're summarizing the whole document as a single vector, and they found that it performed poorly. So that tells us that fine-grained embeddings for each token is important. And point two will be they also did average similarity, and they found that also led to poor performance. And that tells us that actually the maximum similarity metric is important. So it's not just so it tells us the max similarity is important, and that kind of tells us that it's important that each query attends to some document token specifically. Like the token to token interaction is more important than the token to the document interaction. And lastly, they also did query augmentation, which turns out to be important, but I haven't been able to understand and digest this explanation. So yeah. Lastly, that's Colbert. And lastly, I'll just mention reciprocal rank fusion as a side. So if you have multiple re-rankers, you can combine the re-rankers in the following way. One might naively think that we can just combine the ranks by doing a sum, right? So maybe we just sum up the ranking scores of like 1 + 2, 1 + 3. But it turns out that actually weighs like 61 and 62. The difference between 61 and 62 versus like 1 and 2, that actually views them as essentially the same difference, which is not what we want, because we want higher importance on the first and second places, the front few places. So that motivates us to define the combined rank as the reciprocal. So now 1/1 versus 1/2 is very different from 1/61 versus 1/62. And so that's why first rank is in the denominator. And the K is just a parameter to dampen the effect of low rank items. So you don't want like 1/1 to be much better than 1/2. You put usually K is like 60 or something. So that kind of dampens the effect of very low rank items. And yeah, so here are some very interesting resources that I found useful. And yeah, I'll pass the time over to the next person. Thank you.
So before we get to Manas's point, I want to clear a little bit about what Chien Hao was talking about query augmentation, since we didn't get a chance to go through that. So do we know what query augmentation refers to again? Just a quick 1-sentence summary of what query augmentation means. We had a whole lecture on this, right?
Rewriting the query to match method.
Okay, so sometimes we get a query that's not quite exact, or it's sort of an ambiguous. Then what we might do is like try to add more to the query by rewriting it or rephrasing it. And so what Chien Hao said with the Colbert is that we're doing late interaction, which means we take each individual word in the query, we encode it. We don't try to pull it together. So we have basically all these little bits of words in both the document and the query. And we do late interaction. That means that scoring time, we actually calculate the score for all of these things interacting with each other. Whereas in a typical early interaction system, we take the query and build one huge representation for it. Take the document and we build one huge representation for each document, right? So when we talk about query augmentation, what it means is that instead of just using the query directly as given by the user, we can do query augmentation on it, right? So we say, okay, you asked about lost in the middle and mitigations, okay? So I'm going to add a lot of other variations to that, like recovery in the middle, recovery, not just mitigation, you know, other things related to this. Okay, all of these are extra keywords that I'm just going to dump in. And because I'm doing it at late interaction, it's not expensive. I just code all these little vectors. I just keep them around. And then when I do the scoring at late interaction, I just add them in. Okay. Now, late interaction, when we're doing query augmentation, can be done with actual words, like we do rewriting, or it can be done with vectors. So one thing that you can do is you can say, oh, you know, you have lost in the middle of mitigations. That's your query. Okay, what I can do is encode all of these, and then I can take the average of all of these individual words as a sort of centroid, okay, and add that centroid also to the query, right? So then I can do the same type of thing as we talked about before, do the augmentation in lexical space, meaning words, do the augmentation in the vector space, that means separating. Okay, you could also do it with the document side, okay, we're just talking about queries. Okay, so I hope that helps you a little bit.
Thank you. So maybe just one question here. Just now you talked about if the query needs to be packed together. If it's short, you can pack it, right? If it's long, you can cut. And that part I'm not for sure. I think you cut the query.
Yeah, my understanding is that I tried to look it up online. My understanding is that the assumption is that queries are typically not too long. So that's a huge assumption. If the query is very long, then I do think that.
Yeah, because I think that approach to the big assumption is actually you got a relatively stable range, right?
Yeah.
If it's long or short here, even the document also has a challenge. That become like a very difficult situation.
I think the cutting only applies to the query, not the document.
Yeah. Okay, yeah, that's true. Document you can still charm from.
Remember, a lot of these cases, like what Rishabh was talking about earlier, is that we can do pre-filling or pre-fetching because we may know based on interactions from the user or previous interactions, we have some idea of what documents might be relevant, right? So then we can say, we don't care about most of the document space, you know, Wikipedia entries in Swahili, probably we don't need to fetch, right? So we just leave them out. Sure, with queries in Swahili, for example, right? So then we bring the space.
That looks more like a preview for us.
Yeah, so there's a lot of these optimizations. That's why we're talking about it today for class. Okay, so Manas can take it away. I thought, do you have any comments?
Okay, thank you, Professor Mi. I'd like to mention the point since we are talking about efficient re-ranking, I'd like to remind the page 25 as I noted in the Slack channel. I mean, the efficiency of covert can be further improved, such as SIG-IR paper this year, which got the best paper award. So please refer the details in the Slack channel about the efficiency. Thank you.
Okay, yeah, that's a very nice reminder. So we'll take it from here. I'll try to find the paper and then put it up on the side. Okay, thank you so much. Sorry to keep you waiting.
No, yeah. Good. So, hi everyone. In my section, I'll be talking about federated search, and most of this section is going to be on a particular paper about efficient federated search for RAG. To just start off, I think we've all talked about in the beginning that LLMs are powerful, but it's still vulnerable to hallucinations, outdated knowledge, and inconsistencies. And this is where RAG came into picture, wherein we could retrieve relevant documents, and now our responses are grounded in actual evidence. However, the challenge is that in RAG systems, what we're assuming is one big vector database, which is storing all the information. But in real world settings, we have federated setups where it's distributed databases. And there's data in many silos or regions, databases, and different like this should like it's stored across different regions or databases essentially. And centralizing it all into one database might not be possible because of cost, size, latencies, and compliance. And so the problem is essentially how do we retrieve from all these different sources as it is slow and costly? And how can we do RAG well and cheaply when data is distributed? So when we talk about RAG efficiency, it's about retrieving less while maintaining the answer quality. Every retrieval call has cost, latency associated with it, as well as API usage, adding context tokens, and all of that. There has been prior work on RAG router as well as adaptive RAG, asking do I really need to like query the source? But these papers and this previous work, they assumed a single retriever while routing at the document levels. But now we need this for a federated like setup, which is across different, not just on a document level, but across different data. So just a quick recap on how standard RAG works, which we I think seen throughout this course, is that data is created in chunks, then through an embedding model, there's embeddings are created and they're stored in the vector database. And when we get a user query through the embedding model, it's also converted into an embedding. And based on this embedding, we try to retrieve relevant stored embeddings from the vector database, and we retrieve the corresponding data chunks. And now with the retrieve data chunks and the query, we pass it to the LLM, and the user gets the final response. So that's how it's worked so far. And so where does federated search come in? So federated search in classical information retrieval, it means that you broadcast a query to multiple index sources, which could be departmental databases, vertical search engines, and so on, and then you merge all these results. So the key feature here is that it's multiple independent sources and not a monolithic database. And you need to decide which sources to hit and how to aggregate it at the end. So in the context of RAG, federated search means that you have multiple retrieval endpoints, and each is perhaps specialized. So you can have a retrieval endpoint that is specialized for legal things, or say medical things, and so on. And you have to dynamically decide which subset to query. And moving on. So one thing that's covered in the paper is that not all sources are equally useful. So in this diagram, you can see that there are different question sets and there's four different corpora. You can see that PubMed is relevant like most of the time based on the relevance score. However, maybe for the MedQA question set, Stanford's is only the most relevant. Like you can basically, this opens up an opportunity where you can learn which sources are most useful for which query types, and then you can avoid contacting irrelevant corpora, for example. So this brings us to the federated RAG problem. So imagine you're given, not imagine, but you are given a query queue, and you have n available retrieval systems. And the goal here is basically you have to select a subset of these retrieval systems wherein you can maximize the relevance coverage and also minimize the retrieval cost. So there are three challenges here. One is to identify the relevant sources per query. You also have to minimize unnecessary queries, and at the same time, you have to maintain high recall. So one thing to keep in mind is that let's just say that there are k embeddings per retrieval system and there are n retrieval systems. So in total, there are nk embeddings. I'll talk about this a bit later. So yeah, in a federated RAG setup, we have multiple data sources and we need to do distributed retrieval and aggregation. So in the naive approach, you query all the sources and the cost is nk because now there are k embeddings and n retrieval systems. So there is a communication overhead because you have to query all the n servers, and also the latency scales linearly with n, which is not ideal. And there is also a possibility that the LLMs can hallucinate because there is information from irrelevant retrievals. So we need to take a smarter approach where we route the queries selectively, and this will reduce the retrieval cost from nk to mk, where n is lesser than n. So it's just a subset of the retrieval systems. So you're querying the top 10 sources. So the authors in the paper that I mentioned talk about the RAG route, which is a small neural network classifier that decides which sources are relevant given the query embeddings and the summary features of each source. So if you can see over here, there is a query that is passed from the user, and we create a query embedding out of it. Now, what is different in this pipeline is that the query embedding is passed to the router. And after the query embedding is passed to the router, based on the embeddings from the query, as well as knowing some information about the data sources, it provides you information about which of the n data sources are relevant. So let's just say it chooses m out of the n. And now it creates m into k embeddings. And we again have one more step where we filter further to create the top k embeddings. And after this, the data is retrieved and the query is combined with the retrieved data and we get a response. So essentially, the thing about the RAG route is now that we have a router, so we don't query all the end retrievals.
Does that mean that you need to have a kind of a complete set of queries so you can train a model?
Yeah.
Because the query is a little bit of open.
Open.
Right. So it's a bit hard.
Yeah.
To really ensure that that's.
So the router is trained in such a way that it like learns from each query as well as like a neural network. So it needs to keep learning.
Yes, but exactly the problem of the training and machine learning is actually you don't want to you cannot handle the same out of distribution. So that's
an issue. Yeah. That would still be an issue, but this is just like one of the ways. It is an issue. So talking about the router design itself, it is a shallow neural network with 3 layers, and it's all fully connected layers. Each data source, so like 1 to n, they have a pre-computed centroid and statistics, and during training, we label the sources as relevant if their chunks appear in the top k retrieval for that query. And the supervision lets the router learn meaningful query source relevance patterns. And for each candidate data source, the router predicts a probability. So the router training process is that we run global retrieval across all the n into k embeddings, and we reduce it to the top k most relevant ones based on the distance to the query embeddings itself. And after that, we label the query source pairs with like a binary label 1 or 0 based on whether the top k merge results contain embeddings from the given data source. And this is trained with a binary cross entropy with virtual scores. So after the training, during the inference and the routing stage, we embed the query and we're also computing features for each of the data source. Now the router predicts a probability about how relevant that data source is or the retrieval system is. And we select the top m based on if the probability is above a certain threshold. And now we only retrieve from those n relevant retrieval systems, after which we merge, rerank, and pass it to the other. So in the paper that I mentioned, which is the effective federated search for RAG systems, the experimental setup was basically done on this thing called Mirage, which is the medical information RAG evaluation. And it's a medical Q&A set and has 5 fora. And also they did it on MMLU, which is a benchmark that evaluates LLM systems. And the metrics that they use to understand the efficiency of the RAG route are basically the routing accuracy, the retrieval communication volume, and the end-to-end question and answer accuracy. So as you can see over here in this diagram, this is essentially showing the recall percentage, and we can understand that RAG route actually compares well with querying all the sources, and it achieves nearly the same call, proving that it's rarely missing the relevant sources. And recall is computed by comparing the retrieved snippets per question against a set of relevant snippets across all the data sources to establish the graph. In terms of efficiency gains, you can also see here that the RAG route takes much lesser queries compared to the naive approach of querying all the different corpora or retrieval systems. And in the study, it was actually observed that it takes 77.5% fewer queries And also now that you have lesser data to aggregate, it's 76.2% lesser data transfers. And even though we saw such like far fewer queries, the RAG route maintains nearly identical accuracy as you can see. So the RAG of Zopera had around 72.22, but the RAG route had 72.24% accuracy, which shows that the efficiency did not really sacrifice. So in practical deployments such as corporate RAG systems spanning multiple internal knowledge bases, routing can drastically reduce query load as well as cost, which is important because now we require lower bandwidth and compute for cleaner AI because we've all seen how energy intensive all these AI systems are. So efficiency is really crucial here. So yeah, to close it up, I think federated search is one of the steps in RAG, especially for enterprise or multi-domain settings. And RAG route shows that you do not necessarily have to query everything, and intelligent learning routing is the key. And as we deploy LLMs with higher token and API costs, such efficiency strategies are indispensable. So, thank you.
Any questions from us? Okay, the paper that Manas has gone through, we can also put on the Slack, and there are a couple questions that Mariana has put up. So if you'd like to engage that, please do. I think now we'll go over to the last section before we end. That's Yong. Yong, are you online?
Yep, I'm here.
Okay, you can share your screen.
Okay, give me a while.
Yeah. Okay. Okay, while Yong is getting ready, again, just to keep things a little short. We have the RAG notes, the overleaf, which our scribes have been contributing to. We'll be trying to finish that up within the next couple of weeks. All of you who have been contributing will be listed there. And then we'll try to make that an artifact that can go on the website, maybe released to archive. So anyone who wants to go have a look. Okay, so that will be a nice outcome of that. So I'll say it a little bit more later. We'll close up the course. So Yong can take it away.
Okay, yeah. So now I'll be talking about how metadata and filtering can improve rank, mostly in efficiency, but in some cases also in accuracy. So first, what is metadata? I guess dictionary definition is that it's data that provides additional information about a data point itself. So here are some types of relevant metadata that can be used for rank. So first, the most obvious, sort of the classic type of metadata is the baseline information provided for every document, such as the file names, the date that the file was created. Next is structural metadata. So this is more rank related. It's data that captures logical organization of the documents, including fields like the section heading or even the page number in a PDF. And finally, we can also generate metadata when indexing a corpus. So we can use LLMs or other methods to generate data like tags or maybe like perform sentiment analysis on documents to add this metadata. Yeah. So there can be many other types of metadata, and what types of metadata we generate and use usually depends on the application or task. So metadata is used to perform filtering in retrieval pipelines. And filtering is basically removing irrelevant data from our search space or context. The main problem that filtering addresses is caused by having a very big corpus. So having to search through a lot of data introduces high latency and noisy results. Latency is the most obvious issue. Performing a search with any method, be it nearest neighbors or other methods, will obviously take more time with a bigger search space. So filtering narrows down the search space, which then directly increases the search speed. Next, trying to retrieve from a large data set also introduces a lot of noise. I believe this has been discussed quite a bit. And this like the needle in the haystack problem. The bigger the haystack, the harder it is for us to find the correct bunch of hay that contains the needle. So filtering can hopefully help us narrow down and target only the relevant sections, increasing the relevance of the data that we retrieve. And lastly, filtering gives us control over our retrieved results. So for example, recently Google, the Gemini app, introduced a feature where they are able to retrieve from your Google Drive, so documents from your Google Drive. Filtering here is, of course, ensures that one user cannot retrieve another user's documents. And having to look through the whole set of documents stored on Google Drive ever is a very big task, and filtering also helps there. So here is a simple RAG pipeline that illustrates filtering. So on the left here, these are our documents that we want to index, and they will have the metadata attached. So we index them into a vector store, and now at retrieval time, based on the user's query, as per usual, we'll search the database for relevant items. But we have this thing called pre-filtering, which is where we use additional rules to decide where to search or what to search for. So I'll go into more detail on this later. Then after we get our retrieved documents or chunks, this is when we do post-filtering. We take the results of the search and we narrow them down to improve performance. This can include the re-ranking that we discussed just now, and as well as selecting documents that will optimize generation. So how do we do this filtering? Here are some common methods. The simplest is metadata-based pre-filtering. It restricts the search by using structured fields. For example, we only want to search for documents where the year is after 2022. So this can dramatically narrow the search space while enforcing policies. It also significantly cuts down on noise so that our answer generating LLM doesn't need to dig through irrelevant context to find the answer. Next is vector-based pre-filtering. So this method is more general, using coarse ANN or clustering before performing the full search. Usually this uses a lower dimension embeddings or subset indexing to efficiently perform this so-called first round of searching. This method cuts down the number of vectors that we need to compare for the final search, and is useful if we don't have structured metadata or if we don't have well-defined filtering criteria. Next is lexical filtering using methods like BM25 or keyword match to make sure certain terms are present in our retrieved documents. This can be used to remove totally irrelevant topics. Next, hybrid retrieval, where we combine the best of both worlds. So it uses dense, which is semantic, and sparse, which is keyword search together. So this method is available in many vector databases such as Milvus and Elasticsearch. Next, post-filtering and re-ranking, applying the filters after retrieval, refines the results, and it was discussed just now. So finally, there is LLM-generated filters, where we use an LLM to extract the filter constraints from natural queries. I will talk more about this here. So this is sometimes known as self-querying. So a lot of times we want to perform retrieval without explicitly asking the user for filters. Like we don't want the user to have to type in a separate field, what date range they want to query. This is very powerful when the user query has well-defined parameters. Example of how this works is over here. If the user asks for last quarter's reports, we use a LLM, which can be a small and a fast one because this task is quite simple, to extract this data to form a structured query, where in this case we have year 2025 and the third quarter. So many modern RAG pipelines allow this step to be easily integrated. Okay, so now I'll be going through this new method that I saw a paper on, funnel rank. So it tries to combine the benefits of many different filtering methods. So using this method, they achieved a 40% speed up on retrieval times while still maintaining or sometimes even increasing accuracy. So as the name implies, this method works like a funnel. It goes from coarse filtering of many documents down to like text chunk level filtering and ranking. So this graphic shows the difference between classical retrieval and funnel rank. The top section here shows normal flat retrieval is what they call it. So from the corpus, which may have many thousands of documents, we just use vector search to try and find the relevant documents and use them to generate the answer. So for when our corpus is very large with many documents, it can be difficult to find the correct documents, and it takes a lot of time to perform this search. And also, as JF mentioned just now, there's the lost in the middle issue, where if we throw too much context at the LLM, it may overlook the relevant data. So in funnel rank, there are 3 stages. First, during indexing, the documents are clustered. So each cluster is approximately 4,000 tokens. The retriever used in this stage is a sparse retriever such as BM25 to quickly find relevant clusters. This stage aims to effectively handle the long context to maximize answer recall. Next is the pre-ranking stage. So in this stage, dense retriever is used to find related documents from the hundreds of retrieved clusters. So this retrieval is on the 1000 token scale. The goal of this stage is to pinpoint the needle or the document containing the answer from all of the retrieved clusters. And this is the most similar to the classical flat retrieval step. And finally, there's the post-ranking stage. So the retrieved documents are chunked at this stage to passage level, which is around 100 tokens. And this is fed to a special model that ranks these and filters them to provide the final context for answer generation. So this method progressively reduces the scale of the candidates in each search step. And in each step, we also look at much fewer documents and therefore is much faster. This also allows the capacity of retrievers to be increased, effectively like balancing the load when we have a large deployment while maintaining the accuracy. Yeah. Okay, so finally, I will be ending with some practical considerations when we are implementing filtering. Many of these considerations can be, brought over from like classical database systems where filtering is a big matter. Yeah. So first, caching. If users are performing many queries, there's a high chance that these queries are repeated or they overlap. If this is the case, then we can perform caching on the queries to even further speed up the pre-filtering step. Next is parallel filtering. When there's a really, really large amount of data, a common approach is to shard the database to like split it into multiple instances with predefined rules on what data goes where. In this case, we can perform filtering on all these shards at the same time. So this effectively parallelizes the query and it cuts the filter time by a lot. Moving on outside of databases, we have to be aware of the risk of over-filtering, where if we introduce filters that are too strict or that do not align with the user's query, it will cause documents that contain relevant information to be removed in the filtering step, which is not what we want. Yeah. Finally, there are many hyperparameters that we need to tune. So for example, the weightage of dense and sparse retrieval in a hybrid system, tuning the step size of the funnel rack that I mentioned, and also adjusting filters to balance recall and precision. So this is something that needs to be carefully tuned to maximize our performance. Yeah. So that's the end of my lecture. Do you guys have any questions?
Okay, let's thank our speaker. Any notes from Yong? Any questions about filtering? Other parts? Okay, we're almost done. Okay, thanks, Yong. Let's have a hand for all of our speakers today. One final duty is to play Kahoot, right? Yeah. Then we'll have some final words from High Talent. So, I'll share screen. Already get it. I hope this is the right one. I think I clicked it earlier, so let's hope that this is right. I'm referring too much to your scope here. But this is your very last chance to win Kahoot. If you haven't won, this is the chance to do it. More. I'll give you 5 more seconds. Go on. 3, 2, 1. Well, actually, I don't know who's supposed to be narrating. When do encoder-decoder models lose their relative robustness to positional changes in relevant information? Okay, number 2 is correct. And let's go on. DD321 is in front of 909. By using task-specific natural language instructions, HIDE adapts to diverse retrieval domains. True. Okay, so it is, I don't remember, but I guess you can check the media here to remember how it was adapted so that we can get better retrieval results. Okay, Indra is taking over as lead. We have a couple of people catching up. What is the feature of decoder architectures of HyperRAG? Significant additions to the ability to perform bidirectional context analysis, placement of softback attention, potential attention, very attention to memory, or ability to use key value cache. Okay, so it wasn't lost in the hill, right? We got it in ending position. Okay, Nikhil is in front, taking over Indra, and we have number 4 out of 5. 2 questions left. In Federated RAG, what's the main function of the RAG route system? Which one is not RAG? No, rather than list, very sorry, generate kinetic software. Federated chunk of. All right, 13. Okay, we are losing slightly less than half of us. Okay. DD321 has regained top rank. This is it. final question. What are the improvements? This looks like a multi-select, huh? Of using metadata. Good luck. Oh, let's see. National. Yeah, I know many of us thought, oh, someone's going to say all four, right? Okay, well, good try. Okay. Are you curious? I am. Let's see who won today. Okay, DD321, congratulations to you are her, Isha, and Sam. Congratulations. That was the last time you're going to hear this song for a while. Okay, close that out. Okay, as we finish up, I'm gonna send one link to the general channel, which I have been busy preparing. And I'll ask Hi Tyler if he has any points he wants to make to everyone.
I only want to say thank you so much for everyone for the well-prepared slides. I mean, in fact, I learned more than what I contributed. I feel so lucky I got involved in this course. Thank you so much.
Okay, that's great. So Haika has put up a final Slack post to everyone. As you may have heard from us a couple weeks ago, actually more than a couple weeks about 6 weeks ago, we were preparing a new RAG survey and want to collect student feedback from all of you. So the questionnaire is right there. So if you'd like to participate in the questionnaire, please do help out. I also wanted to post a question myself. Know where it went. Oh. Place. So I'll put it back later on. So there is going to be another questionnaire from me about the course. And especially if you're an external student, if you enjoyed participating, please give back to SOC and we make this course free for everyone. It literally costs thousands of dollars of time and energy from your instruction staff. You're getting it for zero. So please help pay it forward, give generously to our bursary funds at SOC so that we can help students do the job that they can. Okay, so thank you very much. And with that, I think we are going to close the course. Last thing I will tell you is that those of you who were in the WING audition, there are some notes that I've written on today's post if you are interested in going to the lab. And then you can complete the formalities there and check us. Okay, there's one last point that I wrote off on projects, which is that we are trying to archive your posters presented yesterday night. So you know your PDF can live forever, even though your posters will be biodegradable. So please help us by going to the drive. You go to the drive, there is now a folder there to collect posters. So you could just drop them in here if you don't mind us getting a copy, especially those of us who might be interested in contacting other authors. I know there was one poster yesterday where the group was very interested to get feedback from one other author. So please help us fill in what you have here and then put it up. Okay, so that's easy to get to because on the general channel, we have the pins to get to the folder, right? So if you go, there is a bookmark here to drive. Once you go to drive, ending up here, click posters and put the stuff in there. It's read only. Okay, that isn't going to be a problem. Okay, so we're going to fix that right now. Okay, and then anyone can edit. So let's see. All right. So on behalf of SOC, thanks to all of you. If you are a student in CP 3108A and B, make sure you have done your hours and so I don't have to chase you. Okay, and with that, we're 20 minutes over time, and good luck to all of our students to take your finals ahead of time, and good luck during. I think that's it for now. Thanks so much. Take care.